Here we have a system of differential equations. We've got two unknown functions, x1 and x2. Presumably they are both functions of some other variable, let's say time. Ideally, we want to know what is x1 as a function of t and what is x2 as a function of t. But all we know about them so far is how their derivatives are related to both values. So how fast x1 changes as time passes depends on the value of x1 right now and the value of x2 right now. And likewise, rate of change of x2 also depends on the value of x1 right now and the value of x2 right now. So these are interdependent functions. Each one influences its own rate of change and the rate of change of the other one as well. This often shows up in situations like, for instance, population dynamics. If you've got populations of two different species that interact with each other. One common example is a predator and a prey, for instance. Then the number of prey animals available influences how much food the predators have available, and the number of predators influences how quickly or slowly the prey population can grow or not. But there's plenty of other examples as well. Anytime you've got two values that are influencing each other. So in this case, this is all we know about these values. And there's various different ways to solve systems of differential equations like this. This problem in particular suggests solving it by substitution. So this is, in some ways, this is very similar to solving just an ordinary system of equations by substitution. You solve one equation for one variable and then plug it back into the other equation. So for instance, what's a variable we could solve for in one of these equations? Yeah, and of course you could solve for x1 or x2. But this problem specifically suggests solve the first equation for x2 and then plug it into the second equation. So we're going to solve for x2 in the first equation. If you isolate x2, what do you get? How would we isolate x2 there? Yeah, negative x1 minus 1/2 of x1, or negative x1 prime. Well, shouldn't we have the whole thing divided by 2, right? Negative x1 prime plus x1 all divided by 2. Or we could just attach the 1/2 coefficient to both of those. Let's say negative 1/2 x1 prime plus 1/2 x1, which means everywhere we see x2, we can replace it with this expression, including, for instance, here. This x2 could be replaced by this whole thing. However, we also have an x2 prime, so we're going to have to write the derivative of x2 as well. If we're defining x2 as negative 1/2 x1 prime plus 1/2 x1, what would we get if we take the derivative of that? If we're taking derivative with respect to t of this whole thing, yeah, we'll have the same coefficients because the derivative doesn't change those coefficients. It's just that we're taking the derivative of each one of these functions. So x1 prime becomes x1 double prime because we're taking the derivative again. So negative 1/2 x1 double prime. And then this x1 just becomes x1 prime. And now we have an expression for x2 in terms of x1 and its derivative, and an expression for x2 prime in terms of x1's derivatives. So we can substitute both of these in for x2 and x2 prime. So we make those substitutions, and that should give us a new differential equation solely in terms of one unknown function, in this case, x1. So let's write that out. x2 prime will replace with this whole thing. And then 3 times x1, we can just leave as it is because it's in terms of x1 already, minus 4 times this whole thing, negative 1/2 x1 prime plus 1/2 x1. So we've now written out the 2 equations with 2 unknowns in terms of one equation with just only one unknown. But what happened to the order of the equation? What's the order of our new differential equation? Yeah, it becomes second order. We had 2 first order equations. By making this substitution, we transform it into 1 second order differential equation. Because in the substitution, we're taking the derivative of something that already has a derivative in it. So we get a second derivative. And the second derivative does make it more complicated to solve. We got to use essentially methods from chapter 3 instead of methods from chapter 2. But by combining it into one equation, we don't have to worry about a system of equations anymore. And we already know how to solve differential equations that are second order and have constant coefficients. So let's lump all this together onto one side of the equation. First of all, simplifying a little bit. Negative 4 times negative 1/2 is positive 2 x1 prime. Negative 4 times 1/2 would be minus 2 x1. And it might help to multiply both sides by, let's multiply both sides by negative 2. That will get rid of the 1/2 and also make this term positive, which might be a little easier to work with. So just multiplying by negative 2 on both sides. Not strictly necessary, but it'll make the coefficients easier to work with. We get positive x1 double prime minus 1 x1 prime equals 3 times negative 2, negative 6 x1 minus 4 x1 prime minus or plus 4 x1. Any questions on that so far? And what else could we do to simplify this? Make it look a little more recognizable. Yeah, if we can move everything to one side so we have just 0 on the other side, that's going to look a lot more like exactly the stuff we were seeing in chapter 3. So let's try that. We can, also the x1 terms we can combine. Negative 6 plus 4 more is just negative 2 x1. So those combine. And yeah, then let's just add 2x1 to both sides, add 4x1 prime to both sides. So we get x1 double prime minus x1 prime plus 4x1 prime becomes plus 3x1 prime, and then plus 2x1. So there it is as a second order linear homogeneous differential equation with constant coefficients, all in this nice, neat, standardized format. Exact same information as the original system of differential equations, we've just written it in a different way, and with only one variable instead of 2. Any questions on that process so far? And then how would you solve a differential equation like this? Second order equation with constant coefficients, what would you usually do there? Yeah, we can make a guess, set up a characteristic equation. And what's our usual guess for an equation like this? What type of function do you expect as the solution to this kind of differential equation? Yeah, it should turn into r squared plus 3r plus 2 as a result of making what guess? Yeah, something with e to the whatever t, e to the rt. We guess that the function that's the solution to this is an exponential function, e to the something t. We plug in e to the rt, and then r e to the rt, and r squared e to the rt for the derivatives. Divide by e to the rt, you're left with a quadratic. And does that factor? Do we have numbers that multiply to 2 and add up to 3? Yeah, r plus 2 plus r times r plus 1 should work fine. So our r values would be -1 and -2. Let's say r1 is -1, r2 is -2. And that gives us our solutions. Because we were guessing e to the rt, we now have the r values. So that means x1, I'm going to call this x1a, let's say, is e to the -1t. And let's say x1b, because I don't want to use x2 because we're already using that up here, is e to the -2t. Does that work? Yeah, so it looks like x1 can be either of these functions. And of course, those are just specific for some specific functions for x1. How would we get the actual general solution for x1? Yeah, superposition. We just take, let's say, c1 times this plus c2 times this. So x1 is c1 e to the -t plus c2 e to the -2t. So we now have a solution for x1. Any questions on that so far? And now that we've got a general solution for x1, how do we find a general solution for x2? Did we have some way of relating x1 and x2 in the first place? Yeah, if we go back to this, the original equations and just plug this in, we already found that x2 has to equal this expression here, -1/2 x1 prime plus 1/2 x1. So if we just plug in what we got for x1 in here, that should give us an expression for x2. So let's try that now that we've got x1. We know that x2, just bring this down here, x2 is equal to -1/2 times x1 prime plus 1/2 times x1. So it's -1/2 times, so let's take the derivative of this. We'll keep the c1 and c2 coefficients, but e to the -t becomes negative e to the -t, still with the coefficient. And then e to the -2t becomes -2 e to the -2t, again, still with the coefficient. So there's the derivative of x1, and then we'll also need 1/2 times x1 itself, exactly as is. And then we can simplify that, combining like terms, specifically combining the e to the -t terms. So we've got a positive 1/2 c1 and another positive 1/2 c1. So that just makes 1 c1 e to the -t. Then we've also got positive 1 c2 plus another 1/2 c2. So that's 3/2 c2. So this should be our general solution for x2. And note that we can't just absorb 3/2 into the constant as we usually would, because these equations are linked together. This c2 is supposed to mean the same variable as this c2. We could, for instance, say, well, let 3/2 c2 equal c3, a new constant. But we want to be able to keep track of how these equations are related to each other. So we should leave this as 3/2 c2 because it's explicitly 3/2 of whatever this coefficient is. Any questions on that so far? And a very useful way of combining these into just one big general solution is we would write x1, x2 as a vector function. We can say vector x is x1 of t, x2 of t. And we know x1 looks like this, and vector x2 looks like this. So if we write that out, we've got c1 e to the negative t plus c2 e to the negative 2t. And then x2 is this, c1 e to the negative t plus 3/2 c2 e to the negative 2t. So that's our solution as a vector function. But an even better way to write this is by splitting up the vectors. We combine both functions, that essentially an x component and a y component, into one vector. But if we split this up based on type of function, like everything that has an e to the negative t plus everything that has an e to the negative 2t. By splitting it up, we can now factor this a little bit more. Because if we just factor, like in this case, we've got c1 e to the negative t in both of these coordinates. So we can factor that out. And what's left if we factor out c1 e to the negative t from this vector? What numbers do we still have here if we factor out c1 e to the negative t from both terms? Like if you've got c1 e to the negative t and you factor out the whole thing, what's left? We factored out the e to the negative t also though, so what's left there? What number would have to go here for this times this times this to equal this? Yeah, just 1. And same thing here, just 1. Because you could think of this as 1 times c1 e to the negative t, 1 times c1 e to the negative t. Factor out the c1 e to the negative t, you're left with just the vector 1, 1. Plus, then we can do the same thing here. If we factor out the c2 and factor out the e to the negative 2t, we're left with just 1 and 3/2. So we can use this as our general solution. And this is typically the sort of format you get for solutions to systems of differential equations. If you got a system of 2 differential equations, 2 unknown functions, your solution is typically going to look like some constant times a constant vector times a function, plus some other constant times a constant vector times a function. So you could say that our specific solutions here, the fundamental set of solutions, would be this, without the c1, but with the vector and the function, and this. So we might call this, let's say, vector xa and vector xb. I usually call them vector x1 and vector x2, but we're already using x1 and x2 for the coordinates, so that might get confusing. But 1, 1 times e to the negative t and 1 3/2 times e to the negative 2t would be a fundamental set of solutions. However, one other thing we can do, any multiple of this will also be a solution. So we could just multiply this whole vector by 2 and make it 2, 3 instead of 1 3/2, because c2 could be anything. So let's modify that. Let's multiply this whole vector by 2 and get 2, 3. And then this would make this c2 divided by 2. But since c2 now just shows up in this one spot, that arbitrary constant divided by 2 is just another arbitrary constant. It's no longer linked to anything else because we've combined it all into one equation. So this, I think, would be the most straightforward way of writing the general solution to this system of differential equations. Any questions on that so far? now that we've got the general solution. Then let's see if we can also find the specific solution, because we have initial conditions. So we should be able to plug those in and find values of C1 and C2. So let's try that out. Using the initial conditions, we can fill in 0 for t everywhere. That just makes this e to the 0, e to the 0, so those are just going to be 1. So we get C1 times 1, 1 times e to the 0 plus C2 times 2, 3 times e to the 0 equals the value of x1 and x2 at time 0, which is just negative 1, 2. So that's the x vector at time 0. And now we've got a system of algebraic equations. You could write this, for instance, as C1 plus 2C2 equals negative 1, C1 plus 3C2 equals 2. And you could use any method you want from linear algebra to deal with that. What would be one way of solving that? If you wanted to find values of C1 and C2, what's one method from, for instance, M22B that you could use to find those? Yeah, you could make an augmented matrix and row reduce to reduce to echelon form. So in this case, that would be 1, 1, 2, 3, augmented with negative 1, 2. Exact same system of equations, just written in a more compact form. And then you could row reduce that. Ideally, the left side of the matrix should turn into the identity matrix, and whatever's left here will be the values of C1 and C2. Plug in those C1 and C2 values here and here, and you'll have the specific solution to this initial value problem. Any other questions on that so far? All right, then let's take a look at the idea of linear independence, because we have two solutions, 1, 1 e to the negative t and 2, 3 e to the negative 2t. If we want to check if those count as linearly dependent or linearly independent, let's go back to the original definition from linear algebra. The whole definition of linear dependence versus independence ultimately goes back to the idea of adding up a linear combination to get 0. So we have, let's say we have some vectors, v1 and v2. And it could be any number of vectors. Let's take a look at just two vectors for the moment. If we take a look at the equation c1 v1 plus c2 v2, in other words, a linear combination of those vectors that happens to add up to 0. What's one value of c1 and c2 that will always make this equation true? Yeah, if c1 and c2 are 0, then of course this is going to be true no matter what v1 and v2 are. So that's always true. That's usually called the trivial solution. The idea of making the coefficients 0, so these add up to 0, is called the trivial solution because yes, it's true, but it doesn't really tell us anything interesting about these vectors. It's just true for all vectors anyway. So the trivial solution always works. The big question is, are there other solutions? Are there other values of c1 and c2 that make these add up to 0? And if there are many solutions, then we say these vectors are linearly dependent. Many solutions, which is going to include the trivial solution, of course. So if this equation has many solutions, in fact, infinitely many, we would say that the vectors are linearly dependent. On the other hand, if the only solution is the trivial solution, if the only way to get them to cancel out is to cheat and use both c values equaling 0, then we say they are independent vectors. The idea of linearly dependent means if we're able to get these to cancel out, blurry, is that just the text suddenly went blurry or what? Does that help? Okay, I'll try to write bigger and see if that works. But yeah, if the idea of adding these vectors together to get 0, if that only works by having C1 and C2 both be 0, that basically means that the vectors are genuinely different. There's no way to get them cancel each other out except by cheating and having the C1 values be both 0. Whereas if there are other solutions, like let's say you find that 5 times one vector plus 3 times the other vector cancels each other out. If they can cancel out like that, that means they're not really different vectors. I mean, they might be different lengths, but in the sense that maybe one of them is just a multiple of the other. Or maybe one of them is able to cancel the other one out because it's really the same idea, same information, but just a different amount of it. So that's linear dependence, if you're able to get them to cancel out in some way. And we can apply this same idea to vector functions. We can check, can we add together these functions, 1, 1 e to the negative t, and 2, 3 e to the negative 2t, and get them to cancel out? Or is the only way to do that by making the constants 0? So let's check that with these vector functions. If we have the vector functions 1, 1 times e to the negative t, and I'm just going to bundle those together. So we've got e to the negative t, e to the negative t. And we've also got the vector 2, 3 times e to the negative 2t. So 2 e to the negative 2t, 3 e to the negative 2t. And the idea here is we want to add those together with some unknown constants, c1 times this one, plus c2 times this one. And we want to know, is it possible to make these add up to the 0 vector? Are there some constants we can assign here that will make these add up to the 0 vector? And do you think that's possible in this case? If you look at either of these coordinates, for instance, is there some way you can get something times e to the negative t plus something times 2 e to the negative 2t? Yeah, that's not going to work, right? There's no way you can get those to add up to 0 because e to the negative 2 and e to the negative 2t are not the same type of function. They are not like terms, so they can't be combined. So that suggests that these are linearly independent vector functions. In fact, that's not only true in general, that's also true for any specific value of t. For instance, if you were to plug in a value of t, like let's say we plug in t equals 0, for instance. If you plug in 0 for t, e to the 0 is just 1, so you get 1, 1, and 2, 3. And even these constant vectors, by plugging in a specific value for t, even those constant vectors are linearly independent. There's no way you can get 1, 1, and 2, 3 to add up to 0, except by cheating and using the trivial solution, where you multiply both of them by 0 first. So not only are these vector functions linearly independent in general, they're also linearly independent at any specific location, any specific t value. So if you were to plug in another t value, let's say you plugged in t equals maybe natural log of 5 or something, you get values for these, and you still get linearly independent vectors. So these vector functions are linearly independent as functions, but also if you plug in any t value, the outputs are also linearly independent. So independent in general and also independent at each t value. Any questions on that so far? And let me look up one other example that I think might highlight the difference there. Let's say we have the vector functions e to the t, 2e to the t, and let's say t e to the t, 2t e to the t. And by the way, when would you expect that to show up? When in, for instance, in chapter 3, when did you notice things like e to the t and t e to the t showing up in a solution? Yeah, this tends to show up in repeated root situations. And we're going to get something similar showing up in a situation similar to that for systems of equations. It's going to end up having some extra complications because it's a system of equations instead of just one equation, but it's a very similar sort of thing. It's a very similar cause. So if we want to check if these are linearly dependent or independent, let's say, yeah, if we take a look at these functions in general, again, if we're saying we have a constant attached to each one, we're adding them together, and we want to know, can we get them to add up to 0? Are there any constants you can attach? Like, let's say we look at just the top row. C1 e to the t plus C2 t e to the t. Is there any way to attach constants to these to get them to add up to 0? Can you have something times e to the t plus something times t e to the t cancel each other out? Yeah, not constants. We could do it by cheating and using C1 being a function. Like we could say, one example would be, let's say C2 equals 1 and C1 equals t. Then we'd have t e to the t, or let's say negative t. Negative t e to the t plus positive t e to the t would cancel out. But you're right, that wouldn't be constants. So we cannot have any constants that make these add up to 0. And same thing with the second row. There are no constants that are going to make these functions add up to 0 because they're not the same type of function. They can't combine as like terms. So in this case, we would say the functions are linearly independent in general for all t being a variable. There is no constants that will make these add up to 0. But if we take a look at a specific t value, let's say maybe let t equal 5. Then these would become C1 times e to the 5, 2e to the 5. And these would become 5e to the 5, and 2 times 5, 10e to the 5. So now if we take a look at each row of this, we would have C1 e to the 5 plus 5C2 e to the 5 equals 0. And likewise, 2 e to the 5 times C1, so 2C1 e to the 5 plus 10C2 e to the 5. Can you find C1 and C2 values that make those equations true? Yeah, that's going to work, right? What would be a C1 value and a C2 value that makes those cancel out? Yeah, if we had 5 times this one, and let's say probably -1 times this one, those would cancel out. So that means that if you plug in a specific t value, then these two vectors become linearly dependent. In fact, this one is just 5 times as big as this one. And if you chose another t value, we'd still get a similar result. Like if we had chosen t equals 4, then this vector would be 4 times as big as this one. Or if we'd chosen t equals 7, this one would be 7 times as big as this one. So if you choose any specific t value, these vectors are linearly dependent. But if you treat t as a variable, if you're looking at all t values, then these vectors are linearly independent. And the heart of this really is that the C1 and C2 values end up depending on t. If we choose a specific t value, then we can find C1 and C2 values that work. But if we choose a different t value, we'd have to use different C1 and C2 values. Every t value, we can find C1 and C2 values that work, but they're going to be different. We cannot find a single set of C1 and C2 values that work for every t value. We'd have to change the values depending on t. So as constant vectors, if you choose a constant value for t, then these vectors are linearly dependent. But if you treat t as a variable, if you treat these as functions, they are linearly independent for all t values, but at any single t value, they become linearly dependent. So there's sort of different levels of linear independence here. Any questions on that so far? And as usual, we want to make sure that the functions we have are linearly independent so that we can cover all possible initial values, so that our general solution really is general, rather than covering only some of the solutions. Any other questions on these ideas in general? Or anything else you'd like to work on? One other thing, has your class gotten into the idea of eigenvectors and eigenvalues at all yet? Eigenvectors and eigenvalues, like from 22A, briefly? Okay. I would recommend doing some review of that, like go back to any notes or textbook you have from 22A and take a look at the section on eigenvectors and eigenvalues, because that's going to become very important for solving systems of equations, or systems of differential equations. The idea is we're going to turn the system of several differential equations into one big differential equation with matrices and vector functions. And it turns out that the solutions are going to depend entirely on the eigenvectors and eigenvalues of the matrix of coefficients. In fact, the solutions we found from substitution can be found, I think, probably in many ways much more quickly and much more efficiently by finding the eigenvalues and eigenvectors of the coefficient matrix. So we'll look into that in the days to come as well. Anyway, let me know if you have any other questions, and I will see you next time. You're welcome.